Hello, wonderful class. At this point, this should be our last quiz before our unit test, depending on when you watch this, which is tomorrow. Yes, there's going to be a little overview video. I don't know. I ramble. Look at our wonderful classmate working so far ahead. How great. So, thank you, whoever you are. If you probably aren't even going to check out this video, but if you ever did, that's awesome. And I hope that independent learning, and if you ever need anything or extension, all of you, if you ever need anything or an extension, just ask me. All right. Notice that's rare. That's rare. Let's just think in percent terms. Okay. 1 divided 262. Can you write that as a percent? Come on, camera. There we go. 0.0038. So technically that's 0% of people are able to do that. No, figuratively that's 0% of people because you move the decimal twice. It's 0.38%, or let's say 0.4% of 1% of people can do that, where they learn independently on their with mathematics, and then they kind of go there. There's a lot of reasons why that happens. Not anything special about the actual composition of their brain. They studied Einstein's brain. Nothing was different, but life experiences were, things that he was encouraged to do, discouraged to do, his individual personality, all of those things kind of play a role in our relationship with mathematics. But, right now, you are in charge. So that's the role that you have. You are in charge of your math future. Whatever your goals are, even if it's just to pass. I just want to be done. You want to be done with high school? Great. If you're going to college, you're going to have to take math in college. So don't give up. Definitely pay attention here so you can just take the math you need and then get your degree and move on to your future, okay? Reach out to me, Mrs. Reynolds. Here, let me show you. Now that we're thinking about that. This, for those of you who take the time to watch these wonderful videos, mediocre videos, to help you understand these ideas, I really do appreciate it, and I care, and I want you to be successful in your math career, whatever you pursue. Bottom line, you can pursue a STEM career. You can. Reach out to me if ever you need anything. Through the years, I've reached out to my old teachers. I've gone back to see my old high school math teacher. If I had a third child who was a male, I would have named him Quentin after my high school math teacher. I just touched base with my old college teacher, my very first calculus teacher, Mr. Martin from Santa Rosa Junior College. And so, just keep in touch. Raquel Reynolds 26@gmail.com. So once my student, always my student. If you need anything, that's going to be my email for quite a long time. Reach out and say hi. If you need help tutoring, let's see if you need to pass college, if you just need to pass a simple test and you're struggling with those ideas, including real estate. I tutored people in math for real estate when I had my real estate license. Whatever it is, reach out to me. But please remember, you can do it. It takes as long as it takes. Don't give up. Break it down into smaller and smaller pieces. Let's keep going, as always. All right. Which graph represents... What am I going to do? Sorry, let's go take a look. Why are we not using these wonderful tools that we have at our disposal, right? If you have internet, if you're seeing this video, you have internet. If you have internet, then you have access to Desmos. If it's restricted for some reason from your family, they should be able to unrestrict this specific calculator, okay? Reach out to me if ever you need help. So let's see if we can copy paste it. I don't think it's going to happen. Why not try it? Always try your ideas. Did it work? Oh, it didn't work. Because we don't have that. That's not going to be right. Well, let's scroll down. It's close. It's not quite right. See, it goes up to like 3 and 4. Let me go like 3. It doesn't go up to 4. So it's kind of close. It's see, where's it cross? At 2? No, see, look, it's not, it doesn't even, so that's kind of good. I look at really, let me zoom out. Nope, let's zoom back in. So it's kind of close, but not really. So what can we do about that? Let's try again. This time I'm going to use this calculator because, see, remember, knowing how to use tools appropriately and strategically. Hide, which doesn't stop the recording. Functions. Very cool. Log base A. Log base A under functions. Scroll down. Scroll to like the middle area. Calculus. Log base A. I wonder if you can just type it. Let's go look. Log base 2. That's fantastic. Thank you, Desmos. Otherwise, we were going to do the change of base formula of x plus 1. Okay. So now that we have this and this lovely tool, is that right? Log base 2 of x plus 1. No, that's still not right. This is not, it's not in the parentheses. So, important. How do we use tools? How do we never let them do the thinking for us? We are in control. I saw this. This is what gave it dead away right there. I saw that and I was like, that is not our graph. And I remember this graph does not cross at the origin. So something is wrong. What do you think's wrong? What do you think's wrong? I see what's wrong, but what do you think is wrong? It's very, look, it's so close. So let me do something. Let's get rid of these. Oh, I got rid of them parentheses. Me and my parentheses. I do like parentheses. Oh, what a pretty name. Okay, sorry. Log base 2 x of x plus 1. Here's our graph. Let's zoom out a little bit. And then we can easily identify, okay, that's our graph. Please use Desmos. Please use Desmos. Think about what each of the parameters do. So at this point, we could even use Desmos to explore. Say we're curious. I'm going to make that an A. I'm going to make this a B. Add sliders. So if I make B, ooh, what's happening there? Right now A is 1. Let's make A 0. So A is 0. So now it's just log base B of x. So now this is just the base changing. Ooh, what? What? Is anyone zoom out? No negatives? Okay. Let's keep going. This is how you use this tool to explore. Let's keep going. Boom, boom, 0. Still negative. All right. As soon as we get positive, our graph reappears. So that's the base, and it changes. So that's, look how B is less than 1. Let's see what happens as we get 1. It disappears. Think about why. Now it's changed directions. Wow, it gets really close. Look at that, how it gets really close. I bet if we got larger than 10, it would be close to the horizontal axis, the x-axis. Okay, let's go to like a reasonable number of 2, right? Why not 2? Log base 2. Now let's change the A. Oh, look at the A value. Look how the A value is kind of messing with our graph. So let's do A. Oh, that's A negative. Oh, cool. Look, we can go down there, down to negative 10. Let's go to 5. What happens when we go to 5? All right. So keep thinking about those ideas. Notice over here, we have a word for this. We have a word for a horizontal asymptote. Look how it's never going to pass the origin. That was just the beginning. We need to keep going. I am using these as mini lessons, so I do appreciate you guys taking the time to watch these. For question 1, please graph it. Log base 2. Okay, B is 2. Let's make x minus 1. A, so minus 1. Scroll up. Oops. I should have zoomed out, scrolled, and then zoomed in. It's faster, right? So again, we have log base 2. That's what I didn't write it. I have the slider. So B equals 2, x, and then A is minus 1. Log base 2, x minus 1. So we're looking for a graph that crosses at 2 sloping upward. That one crosses at 2, but it's backwards. Ah, there it is. Okay. All right, so I'm going to let you look at 3. If you have whatever variation you have, you're still going to need to make sure you're looking at the graph. Question 2, variation 2. What is the domain of the function f of x equals -4 log 2 x plus 3 minus 6? So remember, we've talked about domain. The idea behind domain is what can it be? What values can it be to hold true? What would you do if this was it? If you wanted to get to this question, you didn't look at the lesson, you didn't review any terms, you have no definitions to go on, you don't know anything about logs, why not explore? Why not try to come up with it yourself if you haven't worked through the lesson? If you've worked through the lesson, then you should know what can be in the inside of here. What x values make a logarithm true? Let's go find out. So now I want, let's see, where is this? X plus 3. Well, let's get rid of this. Let's have it back to log base 2. So we're going to explore this idea. Log base 2x. If you already know, that's wonderful. I'm going to actually evaluate some ideas. So I saw something interesting. Remember the asymptote I was saying about the graph? That's something I want to start to associate with this concept of, all right, the logarithm never went past here. Let me just actually put it in there again. If this log base x can never go past here, let me copy this, highlight, Control C, Control V. Let's say, what happens if I look at x? Look how that, like, these are the negative x values over here. What if it's -1? Undefined. I wonder why. What is the logarithmic function? What does it represent? What does it undo? What is it the inverse of? And what does it give us when we put that value there? Remember, the logarithmic function says we're looking for some value, +2, to the exponent x, which equals -1. Is there any possible value of x that would make this statement true? You can now use your calculator. You can use the 2 caret and try some numbers for x to see if you can ever get a negative number. What about 0? Pause it, think about it, but here we go. Undefined? Where's that word again? Mathematicians, they just gave up. They're like, it's too hard. We're just going to undefine it. Well, again, think about this idea of 1 divided by 0, or any number, 1,000,000, 10 divided by 0, right? What's happening when you do 100 divided by 0? It'll also be undefined, but it's because we have to think about what's happening with our numbers. Okay? If we had 100 over x, we're going to have this beautiful graph. Looks something like this. Now, remember the center. Let me turn this off for a second. The center is where the values get closer and closer to 0. We call those limits. We call them limits. We're trying to figure out what's happening to these numbers, really these numbers, when we get an x value that's closer and closer to 0. Well, as we get closer and closer to 0 from the negative x values, right, from the negative numbers, all of a sudden, whoosh, we go straight down to -infinity. And as we go closer and closer to 0 from the positive x, so like instead of -0.1, -0.10, it's the same number, -0.1, -0.1 hundredths, -0.1 thousandths, -0.1 ten thousandths, and 1 millionths, right? 0.0000s. As we get closer and closer and closer and closer to 0, we shoot up very fast. Same idea if we're coming from the positives. If we're at +1/10, +1,000th, positive 1/10,000ths, right? We shoot up, but we go +infinity. The numbers get bigger, actually, as we divide by a smaller number. So keep thinking about that. That's what undefined means. It means something is happening that's not consistent. We can't really define it, but we'll try later on in math with limits. So mathematicians didn't give up. So notice we have this idea that whatever's inside of here cannot equal 0. That's a very consistent idea. Look for those patterns. Look for that repetition. Check what happens when it equals 0 or 1. They're important numbers, 0 and 1. Simple but important. So over here, all that matters is that inside the logarithm, it can't be negative and it can't be equal to 0. So we just look at the x plus 3. We set it equal to 0. Well, x equal to negative 3 can't happen. But here's our very wonderful use of inequalities. Remember, we couldn't even have negative 0.5, negative a half, it's undefined. Negative 1 is undefined. Negative 10 is undefined. So inequalities, right, not an equal symbol, are useful in the sense that we can now write x has to be greater than, strictly greater than negative 3, right? No equal to, no. So that's the usefulness of inequality symbols. Now, let's see what they say, what they want us to do. All numbers greater than negative 3. So they didn't even use a symbol, but they used words that are represented by a symbol. So remember, math is a language, and understanding how to read the functions and the symbols is kind of the biggest hurdle sometimes when it comes to understanding what's happening. So, well done. Take a look at all the other variations. You're just looking to find the domain, what values x can't be, because x is the domain, x is the input, f of x is the range, f of x is the y, the output. Range, output, y, f of x. Domain, x, input. Cool. You can do it. I believe in you. Nice. Okay. All right, moving on. What is the equation of the vertical asymptote of equal h of x equals 6 times log base 2 of x minus 3 minus 5? Well, let's go see if we can't just go graph it and see. But you'll also have rules of graphs. Okay, so now let me wonder how we do like a subscript. Nope, that didn't work. That didn't work. I don't know. Log. Can I go down? Nope, that didn't work. How would I make a subscript? Are there subscript options down here? So I'm going to pause this real quick. All right, so I wanted to see how to make a subscript if it was possible. So let's see if it's possible. It says we can hit shift equal. That did not work. Pause one more time. No, it was me. Control equal. Let's try it. Control equal. No, that didn't work. Okay, so it really says that I should be able to hit a subscript if I hit control equal. But that did not work. It was like command. Function equal? Nope. Alt equal? No. Okay, so control minus. Let's go back to a regular 100%. I'm not sure how to do it, so you need to use this. We're going to delete this. We're going to go to functions. We're going to scroll down until we see the log. There we go, log base A. Now we're going to type 2, right? Now we're going to type 2. This is a graphical method. All right, I can get rid of this. This is a graphical method. We need to make sure we know how to use the technology appropriately and strategically. So let's go look at 6 times log base 2, x minus 3, x minus 5. Okay, that's fine. I need this to go away though, because I need it to be the right parentheses for just log base 2. Okay, notice how the x minus 3 is where the log base 2 is. So where do you think the asymptote's going to be based on what we talked about with domain? I wanted to graph it. This doesn't help you. You can't really tell. Well, if you if you realize that these squares, what they represent, you could tell where the vertical asymptote is, right? Look at that. It's like going down forever. It's like almost straight. It's so amazing to me. It's like making a straight line. This nonsense. It kind of. Is it perfectly straight? I don't know. You'd have to really, really think about that. But isn't that amazing? Where is that vertical asymptote? Right? There's some funny memes. You shall not pass. Like a Lord of the Rings or something, I think. You shall not pass. An asymptote, right? Where is it? And why is it there? Did you see that it is at the line? This is important. X equals 3. Yeah, there's our green line. X equals 3. Yep, there it is. Nicely meshed up. It's beautiful. It's not going to pass, but it's going to get very, very, very close. Looks like it tapers off. Look for those things, those visual things. Okay? Now think back to our domain. Think back to our domain of our logarithmic function. Notice how if x equals 3, the logarithm inside equals 0. We can't have that happen. So it makes sense that an asymptote would show up there because we can get pretty close to 3 and we can get infinitely small and very, very, very close to 3, practically 3, but we cannot ever be 3. So it's not natural that there's going to be this wall that's like, you're 3, I cannot be 3. But I can get super duper close, maybe even touching, 3. I hope that helps. If you want a quick way to identify it, just notice if this is x minus 3, then the asymptote will be at plus 3. What happens if this is at plus 3? Oops, plus 3. Let's look over here. What do you think? X equals negative 3? Let's find out. Yes. Let me turn this one off. Off. Very good. See? Now it's over here at negative 3. So that's the key that you're looking for inside those parentheses to decide where is that asymptote. What happens, though, if this is a 2? Still set it equal to 0, right? If this is a 2, it means 2 times x plus 3 is equal, it will be, wherever that's equal to 0 will be the asymptote. So I would say, what is it, 1.5, right? Because 2 times 1.5 is 3. No, negative 1.5, because 2 times negative 1.5 would be 3, and negative 3 plus 3. There we go. Let me get rid of this one. Let's change this to negative 1.5. No, 1.5. And there you have it. See, negative 1.5. So just remember, right in here, it's got to be equal to 0. And that will figure out where your asymptote, your vertical asymptote is. Notice it's x equals, because it's a vertical line. So it's going to, y can be anything, which is why it's a vertical line. Y can be a million, y can be negative a million, but x will always be negative 1.5. If it were a horizontal asymptote, it'd be like this, because y will always be 3, no matter what x is. At x equals 10, y equals 3. At x equals negative 10, y equals 3. Okay, so y equals is for your horizontal, x equals is for your vertical. If you're in doubt, explore it. Okay. Question 3, variation 3. I say it's at, nice. So take a look at each of your variations. Figure out where that equals 0. That's going to be your vertical asymptote. Which answer best describes the transformation of f of x equals log 2 x minus 5 minus 2 from the parent function g of x log base 2 x? Okay, so if you haven't looked at the rules, because there's going to be a set of rules kind of exactly like we explored in the Desmos activity a few weeks ago, or just last week, about e to the x, no, 2 to the x or 3 to the x, and we try to collect the marbles based on moving different numbers in our e to the x exponential function. Same idea here. Where instead, because this is an inverse, it's a little bit different, but let's go play with these ideas and see if we can't develop the rules. Otherwise, take a look at your sheet, take a look at the lesson that was before this quiz, and in that lesson, they're going to give you the notes. Take a screenshot, better yet, write them down. So now you have all of the notes of what the different parameters, the different numbers inside of the equation, what they do to the graph. Use that list to answer these questions. If you don't have that list, if you're using this as the sole source of your learning and lesson, I encourage exploration. Why not? You get to explore, you get to prove it. We're just going to go use Desmos. Here we go. And I'm just going to copy the whole thing because I want to. I'm going to get rid of this and this. I'm going to put it right here for now. That's fine. So now I'm going to put my parent function, g of x, log base 2 of x. Cool. So this whole thing is just going to become x. I'm going to get rid of that 6. So that's my parent function. Down here, I'm going to copy this. Control copy. Control V. It looks like we're putting a 2. That's cool. Oh, look at that. Wait, I'm going to change this color. Hold on. You can change this color. I think do you hold it down? There we go. You hold it down. Let's make it orange. Blue and orange are my favorite colors. So now we see, wow, that's our first step. All I did was multiply by 2. Look how it changed it. Look how it changed that graph. But we're not done. Let's add this parenthesis. -5. Whoa. Well, look at the asymptote. That makes sense, right? Look at that. The asymptote is now at 5 instead of 0 from our original parent function. All right, what next? -2. All right, let me get rid of all this. We don't need that. -2. -2. Oh, we have this red one. We don't need this red one anymore. That's different because it's log base 10. We needed the function. Remember, function. Look for that one. Okay. So how would I describe this? Before I'm looking at the answers, which you should look at the answers. That's going to help you. It's going to help guide your investigation. But I don't want to look at the answers yet. I just want to kind of talk about it. The x minus 5 moves it. I know it's going to move my vertical asymptote to +5 because that's what will make inside the parentheses equal to 0. What does the -2 do? That's the part that doesn't quite make sense to me. Look like there's a nifty little gap there. Kind of gets closer and closer as we continue. But what in the world did the -2 do? Well, for me, I would just say it shifts it down. How did it shift it down? I'm not really sure. This one crosses at y equals 0. This one crosses at 7. So that's pretty interesting to me. Maybe it would change, right? Because at 5, when x equals 7, we'd have log 2 to log 4 minus 2. So it definitely changed the x-intercept. So I'm not quite sure. Let's keep going. And then this 2. Well, this 2 definitely hardened this curve. This curve is quicker. That's the best way I could explain it. All right, now let's go take a look at the vocabulary that you would have learned if you did the lessons beforehand. Shifted 2 units left and 5 units down. Shifted 5 units right and 2 units down. Let's take a look. Shifted, a shift in graphs, that's how we talk about it, what the different parameters do. We shift things, we shift parabolas, right? Okay. Shifted 1, 2, 3, 4, 5. So it shifted 5 units to the right. What about here? This one's interesting. Don't you think this is interesting? I think this one's interesting. So this one looks like it's causing a shift. What else? 5 units right and 2 units down. 2 units down. That was kind of what I wanted you to see over here. This kind of gap. What is this gap, right? Is there a point where it's exactly at 2 units? All right, so let's think about this one. This is shifted over. Look how it's right here. It's also a perfect little intersection between the point 2, 1. This is 1, 0, then 2, 1. So if we shift everything down to, let me see, down to this, yes, it's not quite visual enough for me. But anyway, which number makes it shift down? Is it that 2 or this minus 2? Which one is it? Okay, really think about those ideas. If you don't know, come over here, copy it. Let's copy it. Control copy, Control V. Let me turn this one off. We have the exact same graph. Let's hit this 2. Oh, see the green? Kind of the harder curve I was talking about? That didn't really help me. What about if I did minus 2? Oh, there you see a shift down, right? Oops. Back to that. Minus 2. It drops it. Okay, it drops it, but it changes 1, 2, 3 for the changes 1, 2, 3 for the x-intercept. Anyway, that's really interesting to me. I'm going to pursue that later. But anyway, so if you don't like the list of examples of what do the parameters do, and you're trying to find where is it in your expression, in your equation, what is it doing, then and you have it with you, right? When I use a recipe or an instruction manual, I have it with me. I look back and forth at it. Pull it up on your phone. If you need to, pull it up on your phone. If you don't like that, explore it. This is a very neat part about math. I'm trying to give you the tools and the encouragement to try the exploratory ideas because research shows that it sticks better because you've owned it. You've been like, oh, that's what it does. I see. Okay. So this would help you. This would guide your discovery. And that's kind of the method. Put the parent function in, make a new function, change each one, maybe change it one at a time if you need to, and then see which one makes the most sense. So whatever idea you have, whatever graph you have, one at a time, change the parameters, okay, and see what's happening to your graph. That's 4, right? That's question 4, yes. Okay, transformations. Given the parent function g of x log base 3x, ooh, let's go graph that one. Let's get rid of these. We've already found this, so we can just highlight right there and type 3. Didn't really change that much, did it? Wanted you to think about that. Because exponential functions are very fascinating to me, and they represent real situations, including money and populations and many things. Which equation is shown in the graph? Okay. Again, you should have your notes from the lesson before this video. In there, they're going to just directly tell you, this is what this one does, this K. This is what this B does. I'm not sure. I didn't actually work through every part of this lesson, so I'm not sure which letters they use, but figure it out based on where they are in the expression. So now we have log base, get out of here. Okay. We have -1, -5. That's helpful. We have x minus 2. The vertical asymptote, I feel like we can do. Right? Let's hit Control Copy. Let's hit Control V. I'm going to put plus 2. Oops. I'm going to put parentheses plus 2. But that's okay. That's part of the exploration process. I tried it. Didn't do it right. Didn't make sense. It was the same asymptote. And I know I was looking specifically for that asymptote change. It didn't work, so I went back and fixed it. Okay. That's pretty good. I knew that much. Let's see what else. How do I get it down here to -1, -5? Well, remember, we just discovered that the shift down was when we did this -2 on that last problem. So let's just try straight at -5. Let's see if that even works. Okay, it did. That didn't help us. They gave us a -1. Okay, let me zoom in. They gave us Where's negative 1? Negative 1, negative 5. Okay, well, there it is. Sometimes that doesn't work. If it doesn't work, try this. X equals negative 1. Now you'll have an intersection point that you can click on. When you have that intersection, Desmos lets you click on the actual point of intersection so you can find out what it is, even if it's a messy decimal. Is that good? Does that make sense? So that's a different way of solving things besides using a list of, hey, inside here is a shift left and right. Outside here is a shift up and down. So what we're looking for, according to what we've explored, is negative 5 is on the outside, x plus 2 is on the inside, and let's go see if there's anything else we need to worry about. That looks good. Let's go see about 7, negative 3. So I'm going to type the line. X equals, what was the x equals? What was the x in the ordered pair? 7. So just type x equals 7. Let's go over here. 7, negative 3. All right. Using tools appropriately and strategically is a very big idea, whether it's math class or work. You're going to be presented technology and tools. How you use them is important. Don't be afraid of them. Try them. You're going to make mistakes. I made mistakes. I just made a mistake when I tried to write this expression, this equation, this function. But I just fixed it. You can always undo it. The hard part is when you do something and you lose your work. It's not saved. It's not saved. That's the hardest. All right, I hope this was a good mini lesson as well as quiz help. I know these are longer than they normally are, but I do appreciate you taking the time to watch these. Think about the big ideas and really pursue that learning. I didn't do play posits, so let me know what you think. Some of you really wanted to play posits because you get those extra 5 points, which I will gladly give you the 5 points. Just say, hey, email me, send me an email. All of you out there, all of my wonderful students who I haven't had the pleasure of meeting in my Class Connects or over email or over phone, please email me, hey, I watched these videos. Can I have those points because you earned them? So thanks for watching, and I will see you soon.